let me continue with the sheet pile, not sheet pile wall. Sheet pile wall we have completed. Last part which I wanted to include in this, it was deep excavation, and for deep excavation actually the issue of lateral pressure will be there. Because of that there may be collapse. So, that part while discussing earth pressure theory, I have discussed partly that up to a certain depth we can excavate without any support, and in fact, beyond that if you want to excavate, if you do not provide any support, then the excavation wall may collapse. So, that is the one we have already discussed, and then I will once again I will repeat that one, and then from there what are the modifications required for deep excavation, that I will try to show. And this is the one perhaps we have discussed, and it is a repetition. Once again you can see that the lateral pressure H 3 lateral pressure H 3 sigma 3 in terms of sigma 1 and cohesion, this is the expression. So, you can see sigma 1 K A minus 2 C root K A, where sigma 1 actually if I change the depth, it will be changing actually. So, it is gamma times H, and you can see that when H becomes 0, then your sigma 3 become negative. Sigma 3 become negative. So, minus 2 C root K, that will be negative pressure here actually is a tension, and soil tension means there will be crack will happen. So, this is the one situation, suppose at surface like that crack may happen, and if you go deeper and deeper, tension may reduce, and at some depth tension may be 0. Okay. So, that means the tension crack can go up to this much. So, to find out that, we have done that the theoretical depth of crack H t can be obtained by equating this expression with 0. So, that is what it is done, and if you do that, then H t expression we are getting equal to 2 C by gamma root K A, and if it is purely cohesive, then this become 1. So, 2 C by gamma itself in fact, and so this is the theoretical depth up to his tension crack reached, and but so since it was a tension, there will be some amount of compression will be. So, because of that we can actually, so this is the diagram, pressure diagram. So, this is minus and this is again plus. So, that means up to this if you excavate, there is no pressure on the wall. So, it will be plus and minus get balanced. So, because of that theoretically we can excavate up to this depth without any support. So, that means depth of excavation without support, unsupported cart. So, unsupported, so our maximum depth of unsupported cart will be equal to twice H t, which is nothing but 4 C by gamma root K A. Okay. So, this is the one. So, that means in any soil if you want to cut without any support for foundation purpose, that is the maximum depth, theoretical depth we can go. But if you want to excavate more than that because of any reason, then you have to do something. That is what we want to discuss in this. And you can see here next slide what I have tried to show here, you can see that shallow excavation can be done without any support, as we have shown theoretically up to some depth we can theoretically up to some depth without any support vertical cut. Suppose if there is a cut is this much depth, and if it is based on the calculation what are the, if it is this much, we may able to do without support. But even if you want to go deeper, sometime if you have space available, Suppose you want to cut excavation up to this, and if space available, then you can have a slope and then also you can go. But many situation you may not have this provision or this facility, or there may be restriction that you have to go to property line is there and you have to excavate very close to that, then you cannot slope and go like this. So, in that case what you have to do, when you have to have deep excavation and almost vertical, then you need to give support. That is the thing. That means, under these circumstances the sides of the excavation have to be made vertical and must usually be supported by bracings. That means, when actually the many building sites extend to the edge of the property line. So, this is the property line and you have to excavate here, and you cannot provide any slope this side or this side maybe you can give, but this side you cannot go. In that case, you have to make vertical with some support. So, this one is shown here. Actually, there are different types of supporting systems are possible. Actually, when the comparatively shallow excavation, suppose 3 to 5 meters, you can see here the common methods of bracing the sides when the depth of excavation does not exceed 3 to 3 meter. Actually, that will be done. Actually, there will be wooden sheets will be inserted, and then there will be some support will be there like that. So, and practice is to drive vertical timber planks known as sheeting along the sides of the excavation. The sheeting is held in place by means of horizontal beams called wales. So, there will be horizontal beams, and then there will be here also the sheeting, and then there will be horizontal beam, and these beams will be supported by a strut. So, this is actually when between up to 3 meter excavation, then this type of wooden plank can be inserted, and then there will be cross beam will be given, that is called wales, and both side will be there, and this both side wales will be supported by the strut. So, that will be done in most of the shallow excavation. This is the figure almost shown similar thing. You can see this side, and this may be black one is maybe well, and this may be strut. But when we have not shown, this is actually a picture of deep excavation, and which is not applicable, but schematically is almost similar. But when it is up to 3 meter, what I have shown here, that you have to insert or drive the sheet pile, then when excavation proceeds, you give the support by wale and then supported by strut. So, like that you can proceed. So, this is one way, but if the excavation is deep, if the deep excavation, you can see again there are when the excavation depth exceeds about 5 to 6 meter, the use of vertical timber sheeting may not be economical, and according to procedure the steel sheet piles are used, that we can see here. This is one shown and this is another shown. Initially here, actually if I take a cross section here, what we can see here actually there is a sheet pile, and then sheet piles verticals like that, and then there is this is well, actually that will be beam like, and then that beam will be again with some hard root, there will be packing will be there, and then this is the strut. Okay. This is one mechanism, and another mechanism is that again if it is then what you can do, you can drive H pile here, some interval H pile, and then behind H pile, just in front of the H pile, there will be lagging. Actually, this is called lagging. There is one line to cover the soil, and that lagging will be thin comparatively, and then over the lagging in some interval there will be wales, that will beam like in vertically, and some interval there will be beams will be there, and those beams again finally will be supported from both sides. So, these are actually studs, and you can see that we can say the H pile, these two lines are showing H pile, behind H pile there will be sheet, and then this is the well, and then this is the strut. So, that means when it is a deep excavation, you have to do this way, that either steel sheet pile and then well and then start, or you can give in some horizontal interval H pile, then there will be lagging, then horizontally in some vertical interval there will be lagging, and then it will be supported by the start. So, when it will be initially it will be drive up to certain depth, and then when excavation will be there from the top, when excavation proceeds and it will go deeper and deeper, then one by one you have to provide the well and start. That is the way actually the support system to be designed, and while designing the support system, that means because of this some load is coming to this start. So, you have to design the start, you have to design the cross section of the start, material you have to select. So, for that you need to find out what is the force coming onto this. So, for that you need to do some analysis. So, that I will try to show in the next slide. You can see here that when there is a deep excavation, suppose of depth h, and this is the side of the excavation, and then different people over the time actually suggested some pressure diagram behind the wall. So, we have actually when there is a retaining wall or sheet pile wall, we have got some different type of pressure diagram, but here actually in the practical work based on experience, the different researcher actually like Tarjagi, Peck and others, they have given actually this is by Peck actually given the pressure diagram behind the excavation, and when it is sand, this is the diagram that is uniform throughout the depth, and the intensity is 0.65 gamma h tan square 45 degrees plus pi by 2. That means, gamma h tan square 45 degree actually in the retaining wall, this tan square 45 degree plus pi by 2 is what? It is nothing but K A, and gamma h is what? Is nothing but the pressure, vertical pressure. So, vertical pressure multiplied by K A, it can be lateral pressure at this point, but instead of linear variation, instead of in the retaining wall linear variation like this 0 here and here actually gamma h K A, generally in a retaining wall, but here actually when sand and excavation is done and behind that sitting, the pressure diagram will be just 65% of that 0.65, and instead of triangular it will become rectangle, that means throughout the depth it will be constant. Then it is steep fissured clay, then your pressure diagram will be something like this. It will be trapezoidal up to 20, if the depth is suppose h, the 1/4 of h will be this linearly varying, and then 50% of half the depth actually from there actually it will be constant, and then again from there up to bottom again it will be linearly decreasing and it will become 0. So, top 1/4 and bottom 1/4 will be top 1/4 from 0 to increase to maximum, and bottom 1/4 actually from the maximum to reach to 0. So, this is the trapezoidal diagram, and this is the things to be remembered. So, when there is a deep excavation, we can assume first this diagram, and then you can find out the intensity of this, what is given actually the value of this maximum value is given 0.2 gamma h to 0.4 gamma h. That means, gamma h is actually actual pressure, vertical pressure, and instead of doing anything, just 20% to 40% of that can be taken as the lateral maximum lateral pressure in this. Okay. So, 0.2 to gamma 0.2 gamma h to 0.4 gamma h, this is based on the judgment of the designer. One can take actually 0.25, one can take 0.3, one can take 0.35. So, between any value based on the type of soil, one can consider this value. Okay. So, this is this diagram to be assumed first, and then post other thing to be calculated. Next, if there is soft to medium clay, then another diagram is suggested, that is actually top 1/4. Top 1/4 height will be linearly varying, and it will be 0 at the surface, and it will be maximum at 0.25 h. So, and then rest of the depth, remaining depth, it will be remaining constant actually. So, you can see from here to here the pressure is constant, and that pressure actually how much actually gamma h minus 4 c. So, the intensity of pressure which to be assumed that is gamma h minus 4 C. Okay. So, when it is a soft to medium clay, and when the steep fissure clay, this is the 1.2 gamma h to 0.4 gamma h, and the type of distribution of pressure behind the excavation is like this. When it is a soft to medium clay, type of distribution of pressure behind the excavation is like this. When it is a sand, the behind the wall behind the excavation, distribution of pressure over the depth will be like this. So, once this is known, and then one can find out the pressure load by further analysis, one can find out the force in the start. So, for that I will go to the next slide. Next slide actually I kept blank, and I will just show that how it will be done. Let me show you this way. Suppose there is a this is the excavation, and your start actually is somewhere here, somewhere here, somewhere here, somewhere here, like that. They are maybe uniformly spaced. Okay. And suppose based on the soil type, the pressure diagram something like this, suppose. Okay. So, that means I will consider now this as a beam, and these are the actually your pressure loading. So, looks like this is a continuous beam, and difficulty solving continuous beam little difficult, and here actually you have to do approximate. So, because of that, you know, real beam type of analysis you need not do. What for simplicity in analysis, what you have to do, if there are more number of supports in between, then internal supports, that means accepting the bottommost and topmost support, other intermediate support we will consider as hinge. If you consider as hinge, this is a hinge and this is the hinge, then in that case what I will do, if I consider hinge, then what I will be doing. So, it will be something like this, and there will be support like this, and this will be one, the in between this one, and then so hinge, since there is a hinge I can break into two parts, and suppose this is A, this is B, this is C, and this is D. Then I can say this is F A, and this is, suppose I can say this I can say A B 1, and this one I can say A B 2, this I can say F C 1, and this I can say F C 2, and this I can say F D. So, because of this, now loading is known actually on this beam. This is now all beams are two supports and simply support type. Okay. Loading are known, and then I can find out this and this, since it is simply supported, I can find this and this, I can find out this and this, I can find out. So, if I do this simplification, that means if I assume the intermediate supports at hinge, then I can break the hinge and I can assume the beam system into three beams like this, and then based on consider equilibrium, that means summation of forces equal to 0 and summation of moments with respect to a point is 0. If I do that, then I can find out all F A, F B 1, F B 2, F C 1, F C 2, and F D, all I can find out. And finally, F A will be F A whatever coming from here, F B will be equal to F B 1 plus F B 2, and F C will be equal to F C 1 plus F C 2, and F D will be equal to whatever I have got. So, F A and F D directly I am getting, and F B and F C I have just summation of these two parts like that. So, it is very simple. So, if you know the depth of the excavation, then and type of soil, then immediately I will get this pressure diagram. Pressure diagram actually, suppose if it is a fissured clay and that soft clay, then actually what will happen? The top 25, this is actually 0.25 H, we know that this is 0.25 H, and this is actually 0.75 H. So, that means, and what is this value? That is actually gamma h minus 4 c if it is a soft clay. So, this intensity I know, this distance I know, again the spacing I know, between the start spacing I know. Then if I assume hinge here, then this entire beam can be, I can modify to this 3 beams, and when it 3 beams, then considering the static equilibrium, I can find out this F A, F B 1, F B 2, F C 1, F C 2 and F D, and then from there I can find out F A, F B, F C, F D. Okay. I hope it is clear enough, very simple analysis. If you go for a continuous beam analysis, it will be quite rigorous, but here actually not necessary, because it is only support system, and so approximate calculation can be based on this can be done, and you will get higher side in fact. So, that is better. So, this is the type of analysis one can do for finding out the start. So, instead of this, suppose if the another excavation is done only sand, in that case your diagram will become something like this. Your diagram will be, as we have shown, sand actually pressure diagram something like this, and starts are like this. Then again this one will be simpler than this actually, and if it is a steep or fissured clay, then your diagram will be something like this. This is the excavation and supports are here. Suppose supports are here, and your diagram will be something like this. So, again similar way, the way I have divided here, this also can be divided considering hinge and here, considering hinge here and here. I can divide the 3 parts, and I can find out the all components, and finally, to find out the actual loading in the start. Okay. Next one, actually as you have mentioned here, actually that when you will excavate deep, and then there is a chance of the weight of soil, if it is soft soil, and then there may be a along some vertical surface it may fail, and this entire mass, this soil mass can try to have tendency of moving upward, and that means bottom can fail actually, heaving can be there, and then finally it can fail. So, that for that analysis actually one can do this, one can find out the factor of safety against heaving or bottom failure. So, for that some temporary some approximate analysis one can do, and that, and for doing that one can do 2 different cases. One is when the clay below the cut is homogeneous at this up to depth equal to 0.7 b, actually that means below this cut is, the cut level is here, and from here actually at least 0.7 b is actually the same homogeneous soil to have actually this type of failure actually. So, that is the thing actually requirement. If it is so, and other alternative what is that, there may be thin, there may be some other hard layer is there before that. So, that is another condition that I will show later on. So, this one actually, so when this mass actually sliding actually from trying to come and move this way, then actually how much is the load A B C D, actually you can see A B C D, how much is the load. So, if it is width is b bar, so gamma h and multiplied by b bar, and if I take unit length, then gamma h b bar is the weight, and this weight partly supported by this shear along this line, shear along, then you can see. So, because of that we can say C times h over the depth actually, and if I take width actually 1. So, that may be, so total loading of soil weight is this gamma h b bar, and it will be partly resisted by C minus C into h. So, that means net loading will be gamma h b bar minus C h. So, if I take b bar into h, so gamma minus C by b bar. So, this way can be written. So, Q actually suppose that is intensity of pressure, that will be Q by b bar, suppose that must. So, actually Q by b multiplied by 1. So, actually perpendicular to the board I can assume length actually 1. So, it will be q by b multiplied by 1, and in that case you can see the q expression for q. So, if I divide by b bar, then become h gamma minus c by b bar. So, this is the expression for small q. That means, because of this, when this entire mass is trying to slide, then at this level what is the pressure it is giving, that is q, and we know that at this level, and what is the ultimate bearing capacity of the soil. Ultimate bearing capacity of the soil for soft soil, generally we know that C times N C, and for soft soil, you know that C value is 5.7 or 5.14, anything then in between you can take. So, 5.7 C, that means your q ultimate is 5.7 C, and actual pressure you are giving this much. You are giving pressure because of this depth of excavation, this much pressure is coming at this level, and bearing capacity at this level is 5.7 C, irrespective of height anything. So, now we have to see, we have to compare this and this, and based on that we can find out what is the factor of safety available. You can see this next slide. You can see that factor of safety will be q u divided by q. Okay. And so, if this q is much smaller than this q ultimate, then it is safe, and if it is this q become much bigger than q this q, then it will be unsafe. So, because of that we find out factor of safety by q u by q. So, the expression is 5.7 C by h gamma minus C by b bar. So, this is the general expression, and because of the geometrical condition, it has been found that b bar cannot be more than 0.7 b. So, if you can b bar can be substituted in this, then your factor of safety expression become 5.7 C divided by h gamma minus C by 0.7 b. So, this is the final expression for factor of safety for a deep excavation against bottom heaving, and for soft clay. When the excavation is done, deep excavation done in a soft clay, then factor of safety against bottom heaving is the expression 5.7 C h gamma minus C by 0.7 b. So, here actually b is the width of the cart, and C is the cohesion of the soil, and your h actually depth of cart or depth of excavation, and gamma is the unit weight of the soil. So, everything is known, one can find out the factor of safety. So, if that situation arises, that soft soil, one can also has to check the factor of safety. Otherwise, we are excavating, but because of the soil movement from like this, it will be moving like this, then this lot of pressure will come on this wall, and some failure may occur. Okay. So, this is one type of factor of safety, as I have mentioned, that if the below the excavation, if the sufficient depth is homogeneous. If it is not so, if the other type, that means this is the one, you can see that hard stratum is there at shallow depth, that so that this entire failure mechanism is not prevented. In that case, you can see that 0.7 b, instead of that I can restrict now d only. So, you can there actually we have shown that b bar we have replaced by 0.7 b. So, there actually instead of 0.7 b, now you can put d, then your expression for factor of safety become 5.7 C h gamma minus C by d. Now, this part actually compared to smaller than this. So, because of that we can simplify this factor of safety equal to 5.7 C divided by gamma h, and you can see, and you can express in some well known term, that is stability number, that is 5.7 by gamma h by C. This is actually stability number. So, 5.7 by n s, this will be s actually 5.7 by n s, smaller movement with smaller value of n s. Actually you can see, that means factor of safety will be more when n s is small, and if the n s is big, then factor of safety will be reduced actually, that, and then that means it will be unsafe. So, that is what one has to find out this stability number and then find out this ratio and see the smaller means more less movement and big means bigger movement and failure. So, with this actually I will let me these are the things actually related to deep excavation we need to know. So, with this perhaps I can stop here and I will take some problem in the next lecture. Thank you.